Hello everyone, thank you for joining. Now this is the second video about Einstein's theory of special theory of relativity. In the first video we talked about a different platform and different observers, and we said that there is no such thing as true velocity, which is fine. This statement will be challenged by Einstein, but we said there is no true velocity, and the more important, the more fundamental question was, can we also say there is no true acceleration? Well, there's a problem. If you remember, we have F is equal to ma. If acceleration is relative, that means the laws of physics is relative, and we don't want that. And in this video, we want to find a reference frame, whoever is in such that acceleration will be the same independent of the observer. So to understand this, let's consider two reference frames. So two people, right? So let's call the first person A with coordinate system xy, and the second person A dashed, coordinate system x dashed and y dashed. And let's say that there is a firecracker somewhere here. Let's say somewhere there. So according to an observer at A, the position of the firecracker, let's call it O, let's say this is R. But according to an observer at A dashed, we get a position vector to be that. Okay, let's call this R dashed. And let's say the distance between A and A dashed is capital R. Okay. And to make this, we don't need to assume that A and A dashed are stationary relative to each other. Let's say that A dashed is indeed moves away from, well, it could move towards as well. It wouldn't change anything, but it moves away from A with some velocity capital V, right? And remember what we're interested in. We're interested in a frame of reference where the laws of physics preserved are protected and laws of physics apply to everyone, right? So we can easily construct an equation. So R is equal to R plus R dashed. This is a vector equation. All we are saying is going from A to O is the same as going from A to A dashed plus A dashed to O. This is a vector equation, right? And this is, so far, it's classical physics. Motion is continuous, space is continuous, time is continuous. So we might as well differentiate it. dr dt is equal to d capital R dt plus dr dashed dt. Okay, so that is the definition of velocity. And that is also a definition of velocity. And the same thing here. Now, one thing to notice here, that if we are observing an object, this here would be the velocity of the object observed by an observer at A, and this would be at A dashed. So V and V dashed, little v and V dashed, little v dashed, are the velocity of the object as seen from two different reference frames. But this capital V has nothing to do with the object. The capital V is how fast one reference frame move away or towards the other reference frame, right? So since we want to preserve acceleration, let's apply derivatives again. So we have dv dt is equal to dv dt plus dv dashed dt. And again, from the definition, this is the acceleration observed by a person at A. And let's talk about this term a bit later. And this would be A dashed observed by a person at A dashed, yeah? And what do we want? We want to preserve, we want to ensure that the laws of physics apply. And how do we assure that? By keeping F equals ma as it is. In other words, acceleration doesn't vary from person to person. So in other words, we want that to equal to that acceleration observed from one reference frame to equal acceleration observed in another reference frame. And therefore, we must have, this must be 0. Yeah. So, in other words, what we require is we require dv dt to be 0. Now, what does it mean dv dt to be 0? Well, remember v is this v here. How far and how fast, one reference frame move away from or closer to another reference frame. So, in other words, we want this v to be constant. If v is constant, then Newton's equations of law are valid. Yeah, the laws of physics apply to everyone, all the observers. Okay. So from here we can build on the Galilean principle of relativity, which states that the Newton's laws are valid in inertial reference frame. Now, what does inertial reference frame mean? So let me write here inertial reference frames. Well, inertial reference frame simply means that any reference frame that is traveling at constant speed, at constant direction, or it could be stationary as well. Yeah. So in other words, constant velocity. So velocity has to be constant. So if you have so many different reference frames, 1, 2 there, 3 there, and so on, as long as the velocity of these reference frames relative to each other is constant, that means we are in an inertial reference frames, and the Galilean principle of relativity says that given that we are in inertial reference frames, Newton's laws are valid. Now, that is the crucial thing. Right. The first thing that comes to mind, of course, what if reference frames are accelerating with respect to one another? What is there is some form of acceleration? What's going to happen? Well, that would require Einstein, that would require general theory of relativity. Before we get there, we need to understand the special theory of relativity. As the name suggests, special means it's a special case of general theory of relativity, where we're dealing with inertial reference frames. Okay, well, yeah, so we found reference frames such that the laws of physics are valid. Newton's laws are valid. Now, in the next video, we start looking at where this approach starts to fail when we consider rather than bicycles and cars and so on. When we consider a light, when light goes from A to B, what happens and how things require modification. And we also start getting an intuition about Einstein's genius and how he dealt with these problems. Okay, so thank you for joining, and I look forward to seeing you in my third video on Einstein's special theory of relativity. Thank you.